Hello, friends. Welcome to another class on special relativity that we are going to be getting done today. Just a quick reminder, the traffic light. Oh, crud, I did not post the traffic light. Okay, I'm going to post the traffic light like right after class. It's very similar to the one in the optics section in which you go through and think of things that are red, yellow, and green, and you grade yourself basically. And that is for Friday, but of course, leading up to that, homework 5 and celebration 2 are going to be Thursday, which, as it turns out, is tomorrow by my time right now. So, good. Hopefully, those are going well, and we will go from there. We were talking about special relativity. And so we hit upon the streetlight turning on problem. Right, that's where we were. We're at the streetlight turning on problem. So let me see if I cannot just pull up the picture I took. Oops, where'd that go? Okay. So I drew a picture yesterday, and it looked, let's see if I can reproduce it. It looks something like this. And time. X. And we're going to have a person standing here. And we had lights. All right, and they were 1, 2, 3, 4, and 5. And then we said, okay, I'm going to make a dot on the space-time diagram here to let you know where they are. Okay, so let's see, I did 3. Oh, whoops, I got them backwards. All right, I guess I'm just gonna reverse the numbering and the lettering apparently. Where was this one? Like here? All right, something like that. And there was a car involved. We had somebody in a car moving past at speed v, and so we said, okay, let's draw the axes for those folks. And we decided that I should use a straight edge. That's what we decided. Okay, that's what we decided. I remember that we decided that. All right. So we'll do T prime here. That's the time axis of the car. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Whoops, a daisy. All right, so we had something kind of like that for the car space axis. Okay. Hopefully that looks something like what we came up with last time. It might not be completely exact, but hopefully the flavor is palatable. Now, the question was that I left you with at that point was, in the Earth frame, according to this person who's stationary with respect to lights number 1, 2, 3, 4, and 5, in what order do they turn on? And furthermore, how would you have determined the order that they turn on? So hopefully you had a little bit of time to think about that. So let's take a look at what we have going here. If I'm the person standing here, then my axes are the unprimed axes, X and T here. So in order to measure things that happen at the same time, how do I do that? In other words, in the TX frame, what are lines of basically constant time? Well, for example, the time all along the x-axis here is 0. No matter where I'm at, if I'm over there, if I'm over here, if I'm over here, or if I'm right here, the time is 0 at all of those points. If I draw another line that is parallel with that somewhere up here, then I'm going to say, well, the time up here is, I don't know, 5. But it's all 5 all along this line up here, okay? Therefore, in order to measure, or say, in order to determine if things happen at the same time, then we look at lines that are parallel with the space axis. Okay? That's a fundamental piece that I want you to just keep in your mind for a minute. If you want to look at things that happen at the same time, you look at lines parallel with the space axis. So if I'm this person standing here judging, oh, well, which light turned on first, all I got to do is think about here's how I do it in my head. I take the ruler here and I just go parallel with the space axis here, and I just go up. What's the one I reach first? C. And then what do I reach? I reach A and D, and then I reach E, and then I reach B. Therefore, the order, according to someone who is standing here, the order should be the order should be well, let me do it actually next to this person. Let's do it over here. The order should be, what did I say? C, and then A and D, E, and then B. And B is last. All right. Next question is, if I'm in the car, what's the order I see? Okay, this is basically asking the fundamental question of relativity. In other words, what does it look like if I'm doing this motion? And I'm looking at the same thing. What does it look like from that perspective? Right? That's exactly what we're doing. This is the fundamental relativity question. So what we have here is the same exact situation that we had last time. Now, in this case, the blue axes here are the car time and space axes. But the same principle holds, that same fundamental idea I just told you. If I want to look at lines of constant time, in other words, lines on which all points have the same time, I have to use parallel with the space axis. So I have to start by going like this and then going like this, okay? I have to look at lines parallel with the x prime axis now. And now, according to someone in the car, all things along the x prime axis happen at t prime equals 0. And therefore, if I go up to here and t prime equals 5, well, t prime equals 5 all along that, right? So all I have to do is think about taking this thing and just moving it up, just like that. So it looks like, well, definitely C is first, right? C is definitely first. So as it looks like, I could say D and E are just about simultaneous. That's what it's looking like. I like D and E might be simultaneous. I kind of like that. All right, so we've got C coming on first. I've got D and E. And then as I move up like this, I will hit A, and then I will hit B. So that's a pretty different set of, that's a different answer, different set of results than I had before. Certainly C and B are the outer and the inner, those are the same. But as far as the inner ones and their turning ons, you can see that these two, which were simultaneous to the Earth observer, are definitely not simultaneous to the car observer. right? And those are definitely not at the same time. And I think D and E looked pretty good for that. I mean, I could go D first, possibly, depends, but yeah, I don't know. I think it's pretty close. I'm just going to call them good. That is how you judge simultaneity. All right. And this is a very important key to reading space-time diagrams, is judging either when something happened relative to something else, or did they happen at the same time. Notice, and this is a key piece to special relativity, notice the loss of simultaneity from one frame to another. In other words, things that happen simultaneously in this frame do not happen simultaneously in that frame, and vice versa. That's a key piece. Actually, it's a very historically interesting piece, because if you, and this, by the way, has been done, if you kind of disregard the diagrams and disregard what it kind of looks like, so you can definitely see that things aren't simultaneous as you move around on the space-time diagram. If you don't draw this, and then you forget that simultaneity is a frame-dependent quantity, you can actually disprove the special relativity. You can disprove it and say it's not correct. Now, as I said, I think in the first class on this, which I don't remember if I did or not, but I'll just say it again here. Almost every day in large particle colliders, such as, well, we're here in the coast of California, so Stanford has a linear, the SLAC accelerator, which is a few miles north of here. There's one in Chicago, in Batavia, or really Batavia, Illinois, called Fermilab. There's, of course, one on the Swiss-French border, known as the LHC, CERN. The job of these things is to accelerate particles, and in some cases in a circle, in some cases straight lines. But the job of these things is to get these things going to significant fractions of light speed, like 0.99999, right? Lots of nines. And when they do that, we can assess what they're seeing. And I don't mean seeing, but what does it look like from that perspective? And we find that special relativity seems to work correctly in terms of describing what the results are and why. And we can look to this as to why this is happening. So special relativity has a very solid experimental basis. And it has been done in the past that someone has forgotten about simultaneity and disproved special relativity, much to the amusement of Einstein, who was the one who pointed out his problem. Anyways, so hopefully that helps. Just remember that you're looking at lines of constant time being parallel with the axis that constitutes the space part of the space-time diagram. All right. Likewise, vice versa is also true. If I were interested in things that happened at the same position, I would go parallel with the time axis. So I could say, oh, I want to know, is there anything that's at the same position as light number 2? Well, no, there isn't. Okay, what about, right, now if I'm interested in anything that's a position of light number 2, no, there's nothing. Well, light number 2 is not moving like that, but the point is that the axes give us the ability to kind of set up a grid on this, and the grid for the Earth observer is exactly as it's seen here on the board, but then the grid for the moving observer, moving relative to Earth, comes out skewed, right? So it would come out looking something like, right? You'd have something that looks kind of like that for, oh, well, I didn't quite get it, but hopefully, imagine that those are parallel with the axes that I have. Okay. But that's what coordinates now look like. Okay, so that's the first part to interpreting space-time diagrams. Um, the second part is if you look at a point on the space-time diagram, and I'm going to take a point, let's see if I have do I have a convenient one where they overlap? It doesn't look like it. This one's close, so let's just say like here. Nice big dot. I'm going to look at that point right there, okay, right here. And I'm going to ask some questions about that point. Because we're looking at this on two-dimensional paper, the visuality, I don't even know if that's a word, visually it looks like there's a distance, just like there would be, how do I want to say this? There's a distance from the origin to this point, just as if we're right. It's Cartesian coordinates, right? Just forget the skewed things for a sec. Just look at the outside ones. And if I want the distance to that point, I could certainly draw a line which connected that point and the origin, right? I could draw this line right here, which goes from there to there. And I'm going to do that now, and there, that's what it looks like. There's a, right? And we'd say, okay, well, no matter what you do to your axes, as long as the origin stays there, excuse me. If, for example, I turned my axes really crazily or something, that distance would not change, right? Because there's a point there and there's a point there, and the distance between those points we know by Pythagorean, right? Because we would just go square root of the whatnot with the hypotenuse and the blah, 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 all right? So that is basically like saying, I'm going to measure the distance between, I don't know, you could find two fixed points. Like I'm going to measure the distance between San Francisco and Los Angeles, okay? From here, and I'm going to say, okay, from here, I'm at the origin here at Cabrillo, and San Francisco is located at XY that way, and LA is located at XY that way, and then I could figure out the distance between the two. Now, someone else who is maybe in closer to LA than I am, maybe you're in, for example, oh, let's pick somewhere nice. What's somewhere nice? Santa Barbara. Santa Barbara is nice. And you'd say, okay, from my perspective, if this is 0, then the coordinates of LA are, you see you're standing in Santa Barbara, so LA is right there. And then San Francisco is way over there, right? And the coordinates are totally different, right? Completely different XY coordinates from what I had here at Cabrillo. But you would still find that the distance between San Francisco and LA are the same. Okay, that is exactly like taking these coordinates here, the Earth observer's coordinates, and rotating them around, right? If I rotate these around, I'm going to change the coordinates of this point based on how I draw my axes relative to the origin and the point, right? But this purple line does not change. Okay, hopefully that makes sense. There is an analogous quantity in special relativity. In other words, it doesn't matter what frame of reference you are in, whether you be at rest with respect to Earth, moving with respect to Earth, moving that way with respect to Earth, whatever you're doing. There is a quantity which everyone agrees upon, and I want to introduce you to this quantity because I think it's fundamental to special relativity, not only understanding it, but also calculations. So in a 2D sense, because we're looking at these space-time diagrams in a 2D sense, we see the Pythagorean geometry, right? We see all of the usual triangle geometry that we're used to seeing that is true for flat spaces, okay? In other words, anytime I draw a triangle on a flat 2D piece of paper, I will measure the angles, which add up to 180 degrees. If it's a right angle triangle, then I will be able to say that Pythagorean is true, right? And I'd be able to do all this stuff. As an example, let me introduce you to the surface of Earth, in which you could draw a triangle which has basically 3 right angles, right? You could think of the geometry on Earth. Here's Earth, and it's curved, right? The surface is curved like this, such that if I started up here and I walked down this thing here to the equator, I would have a 90-degree angle between myself and the equator. I'm going to walk directly along the equator here, and then I'm going to do the exact same thing, but just return to the North Pole there, where I'm going to have a 90-degree angle here and a 90-degree angle there. So you can have multiple 90-degree angle triangles if you're walking around on Earth, right? Especially if you make right? All you got to do is make a quarter circle around the equator, and then you've got 90-degree angles everywhere. So the Euclidean, that's the word I've been looking for, the Pythagorean theorem is true in Euclidean space. What we're seeing is the Euclidean geometry. Because it's a flat surface, this is not true in special relativity. There is a different way of doing the distance between 2 points in relativity, because the space isn't flat, and that's a discussion for a whole nother class on stuff like this, in which you dive more deeply into it, but we only have certain time, so we're going to get after it this way. The idea here is that Euclidean geometry is not valid, even though it's what we see on the paper, all right? So it's very easy to get yourself tricked into thinking, oh yeah, all I got to do is take a squared plus b squared and get c squared, and I'll be fine. But unfortunately, that's not true. Euclidean geometry is not valid in special relativity. And by the way, just a quick note on special relativity. Typically, it's called special relativity. It's also called the theory of special relativity, or if you like a lot more words, the theory of special relativity, which is what I just said, the special theory of relativity. That's what I don't know. I maybe said one or the other, anyways, whatever. You can use those, or you can just use SR as the abbreviation. And under no circumstance should you ever call it special rel. That is, you just end up, and the reason I know this is because I've interacted with people who did that, and it was in a room full of people, and I went and interviewed every other person who was in the room, and there was a 100% agreement that the person who used the term special rel was an asshole. So I don't want you to fall into that. It's a warning. I'm just passing on information. I don't want you to fall into the trap, and then people look at you that way. So anyway, just letting you know that. Hopefully that's helpful. We have to use a different method than Pythagorean theorem for finding the distance between these 2 points. This distance is known as the interval. Actually, it's known as the space-time interval. I'll give it the full name, the space-time interval. I will just refer to it as the interval, the space-time interval. Looks like it is the hypotenuse of a triangle, but and therefore it looks like it should be longer than either of the 2 legs, but it isn't necessarily that way. The space-time interval is not the longest leg. I should qualify this by saying it's not always. Okay, not always. But you should be prepared to look at this, okay? I'll draw this in for you. You should be prepared to look at this, all right, and then all the way back here. You should be able prepared to look at this triangle and say, this is not the longest leg. This is not the longest side of the triangle. And that's what I mean. Euclidean geometry fools our eyes into looking at this and thinking, oh, it's a regular triangle. It's not. So I'm just trying to let you know this. Okay, if Euclidean geometry is not valid, what is valid? Well, without going into a whole bunch of detail on what's going on here, what is valid is it is hyperbolic geometry. So here we can talk about the way to mathematically represent a hyperbola. And it's just very difficult to represent hyperbolic geometry on a flat piece of paper. So it fools your eyes into thinking that it is really a regular Pythagorean triangle, when in fact it is not. Okay, so the hyperbolic geometry of spacetime tells us that the interval can be calculated by the equation of a hyperbola. The interval, incidentally, is known as, I think I usually call it delta S. I guess you could also just call it S. I'm kind of not entirely sure why I have the delta in here. S. I'm just going to go with S. I think we can go with S. So the interval here is calculated by doing the square of it should be the interval squared is equal to t squared minus x squared. Now, you'd say, wait a sec, units? We can't do this. T squared, x squared? Well, remember we set c equal to 1 so that the speed units kind of disappeared. In doing that, we set a meter equal to a certain number of seconds. So they're kind of equivalent at this point. But if you don't like that, then what you can always do is insert a small little beta in here, a v over c. If you don't like this, then is this disagreeable to you? Then use, instead of t, use beta t, which is v over c times t. Or actually, I guess just use v times t. Well, anyways, whatever, something like this, where you can say that it's really a distance axis. So you got a distance axis this way and a distance axis this way, and if that helps. I just prefer the easy way, and it's easy for me to say this because I've obviously got years of experience thinking about it this way. But when c is equal to 1, it's just so much easier. T and x do actually have the same units. And here's what I mean. For example, imagine that we eliminate the second. We eliminate the time, and instead of time, we're going to talk about the distance light travels. So in 1 second, we're just going to say 1 second is represented by 3 times 10 to the 8th meters. Okay, so how many meters did you travel when light went 3 times 10 to the 8th meters? So you see what I'm doing? I'm kind of taking the time unit and turning it into an equivalent distance unit, kind of by doing something like this. or CT, right? Same idea. I guess actually, oh yeah, I guess actually I should say CT here, not VT. Actually, you know what? I should just erase all this. I should just erase all this. You should too, and just use CT. That's what you should do. See, it's been so long since I thought of this. CT is the equivalent. So that turns the time axis into a distance axis. Okay, sorry, I got all that wrong. Get rid of all that and replace it with this. That way you're talking about a number of, say, meters traveled compared to the number of meters light traveled in that same amount of time. Okay, and that way you have put t and x on the same footing unit-wise, and then doing stuff like this is totally fine. If you're not happy with that, then whenever I have a t, just replace it with ct. Okay, so you would have c here, and then the whole thing would be squared, so you'd have c squared t squared minus x squared, and you can do that with your axes too. I'm going to leave that to you. I'm going to do it with c equal to 1, and we're going to go forward that way. When we need to, then we just reinterpret the results. All right, so this is the interval, and this is the kind of quote-unquote distance between points in special relativity. This is the equivalent to the Pythagorean distance in Euclidean geometry. Let me put this to use here, and let's do an example. And then I want to get back to talking about simultaneity from the special relativity standpoint. All right. Let's imagine that I want to take a space trip. I can't travel through space only. A space-time trip. I'm a traveler in space-time after all. Let's imagine I'm taking a trip to a faraway distant star. And the star is so far away that I can't get there in my lifetime unless I travel really, really super fast. So my question is, how fast do I have to travel to get there? All right. Let's get rid of this too. And I want to use the interval to be able to do these calculations. All right, let's suppose that I'm just going to use the example of Andromeda Galaxy. I think that's the easiest thing to do. Let's use the Andromeda Galaxy. I'm going to travel to Andromeda. I'm going to travel to the Andromeda Galaxy. It's the nearest galaxy to us. It happens to be to one digit, about 2 million light years away from us. If you are not familiar with the light year distant, if you are not familiar with the light year, this is basically the exact same thing as a CT measurement. In other words, it's how far light travels in 1 year. So just imagine taking your laser beam, going boop, and then tracking 12 months and going, okay, how far did it go? You can imagine it went a fairly long way. And if you do 2 million of those, you'll be at Andromeda, which is fairly close by astronomical standards, but nonetheless, it's fairly far away for us. So let's do this. Let's imagine that I'm going to take a trip to Andromeda, and I am going to travel a certain speed. Okay, and then the question is, for example, how much time does it take me? All right. Suppose if I travel at a speed of, I guess let's just go with 0.9. 90% light speed. That's pretty good, right? I mean, sheesh. That's way faster than anybody's ever gone. I'm going to travel at 0.9. How much time does it take me? All I'm doing is leaving Earth, blasting off, going off to Andromeda. I don't want to know how much time it takes me. Now, the thing I haven't told you is from whose perspective, right? A lot of special relativity, a lot of the mix-ups in special relativity happen because of either assuming something was from someone's viewpoint when it wasn't, or mixing up viewpoints somehow. It's really important to keep viewpoints separate. Therefore, when I write something like Andromeda Galaxy is 2 million light years distant, oh yeah? According to who? According to whom? Who says that? That is according to Earth's perspective. That, right? This is our measurement of distance from here to there. This is an Earth quantity, so it's important that I note that. Why? Because I'm going to be in a rocket ship traveling at 0.9 light speed, right? To try and get there. The question then is, how much time does it take me? According to whom? Well, let's start by finding out what Earth's time, how much time by Earth clock is it going to take for me to get there? Let's start with Earth first. So first we're going to look at Earth clocks. And second, we'll look at rocket clocks. I feel like my pen's running out. Can you still see it? Fair enough, but I'm going to put that one on the back burner here. All right. If you noticed on that space-time diagram I drew, when I found that point right here, that point had different coordinates based on the xt axis and the x prime t prime axes. This is exactly the same idea as I was just talking to you about me measuring the position of San Francisco and Los Angeles from where I am versus someone in Santa Barbara. What are the coordinates to San Francisco and what are the coordinates of Los Angeles? Actually, it'd be even better if I moved to like San Diego. Then you go Los Angeles and then San Francisco, right? And it'd be really way different then, right? So when I look at the coordinates of that big dot that I made on the spacetime diagram, those don't have, the xt axes have different coordinates than the x prime t prime axes. So we should expect that these two answers should be different according to who's asking the question, because they're going to be different axes, and therefore their coordinates of the point, the point on the space-time diagram when I land at Andromeda is going to be described differently depending on the axes that you're using, okay? And that means, are you on Earth, do you have these sets of axes, or are you on the rocket and you have those set of axes, okay? Okay, let's start with the Earth clock. This is, I think, a fairly straightforward calculation. So, if I think about how much time is going to pass on Earth, I can say that the time, I'll just call it delta t Earth. I'll call it delta t with a bar, like one of those evaluation bars that you use on the end of integrations. E for Earth and R for rocket. All right, so that time should be the distance divided by the speed, right? Because we know the distance in Earth in Earth's reference frame, and I'm going 0.9, I'm also going to agree that Earth is moving that way at 0.9, so I'll have the same speed. That means I should be able to say that the distance, I'm going to call it x Earth, or delta x Earth divided by v should be the time. All right. Now, I've done this in units which are going to make it pretty easy to see what the answer should be. I mean, I think, because if I was traveling at light speed, it would take me 2 million years. So if I go 2 million light years divided by 1, then that would be 2 million years. If I go 2 million divided by 0.9, I'm going to get some number bigger than 2 million, and that's going to tell me how many years it's going to be. And that's a lot, right? Isn't that too many? This is 2 times 10 to the 6th light years. I'm just going to put light. I'm just going to put C for light, CY. Light years. I could use LY, but you could do this. Watch. Divided by 0.9. But what is 0.9 really? It's 0.9 C. So if you're using my disagree units here, then you would do this. Oh, you probably can't see that unless I stand right here. Okay. Then the C's cancel. Because this is a speed in terms of C, and that's a distance in terms of C, and that C is the same one, so those cancel out. And it's 2 times 10 to the 6 divided by 0.9, right? So I'm going to get some number here. I don't actually remember what it's going to be. It's going to be 2.7. I don't know. 2. I don't know. Whatever it is. I'm going to say it's 2.2 million years. All right. Whatever it is. Okay, I'll find out what it is. Sheesh, you people drive a hard bargain. Yeah, 2.2. Why do I second guess myself? All right, 2.2 times 10 to the 6. So we'll go, that's how many years would elapse here on Earth by the time I get to Andromeda. Now let's look at it by rocket clock time. Rocket clock time, how do we do that? Okay, well, fundamental thing about doing special relativity calculations, about to tell you right now, whenever you do a calculation like this, the reference frame who's doing the measuring of these things had better be the same. You cannot be calculating the rocket time by using Earth distance. And likewise, you cannot be calculating Earth time by using rocket distance. Remember, those coordinates are different. They belong to different axes. So every time you do a calculation, it had better be Earth, Earth when you set it up. You might mix them in order to find out something, but when you set it up, it should be Earth, Earth, or rocket, rocket. All right, and you're going to see the same thing here. Earth, Earth, rocket, rocket, not Earth, rocket, rocket, Earth, or something like this, okay? So let's look at this. I want to use the interval to try and find the answer to, so check, we got that one. I want to find the answer to the second one by rocket time. I want to use the interval to do this. How can I do that? Well, here's how you do it. The interval s squared, okay, is the same for every observer. And that is because it links two things that happened, a point on the space-time diagram to another point on the space-time diagram. And the point of me leaving Earth is something that happened, and the point of me arriving at Andromeda is something that happened. Everybody agrees on these points. Everybody agrees on the distance between the 2 points, not literal distance. I mean, the interval space-time distance between the 2 points. So this is how you calculate that. You say, well, I'm going to take t squared here on Earth minus x squared here on Earth. that should be equal to t squared on the rocket minus x squared on the rocket. T rocket squared minus x rocket squared, like so. Okay. So I'm using the interval applied to the Earth frame and setting it equal to the interval as applied to the rocket frame. This is what I'm talking about. Earth, Earth, rocket, rocket. Not Earth, rocket, rocket, Earth. No, 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 no. You don't do that. Well, at least don't set it up that way. Okay. Great news. We know the time on Earth that it takes me to go from there to there. We know the distance between the 2 points there to there. So this, we're all good. We've set it all up. Okay. Here's where the thinking about where you are starts coming into play. I spent a little bit of time talking about this yesterday, and now I'm about to put it into action, and you're going to say, huh? All right. The time on the rocket, this is what we want. I'm trying to solve for this. The problem is I've got this thing hanging out here. I need to figure out what the x distance is between Earth and Andromeda according to the rocket. Okay. So here's where the interesting bit comes in about, are you moving? Did I get on the rocket and blast off? Well, that's not the question I want to ask. Did I get on the rocket and move? That's the question I want to ask. Because blasting off, you can tell. Everybody can tell you're blasting off. I don't want to ask that question. I want to ask the question, am I moving? When I'm on the rocket, am I moving towards Andromeda? The answer is no. I am not moving towards Andromeda when I'm on the rocket. But, you say, how can you not be moving to Andromeda? I'm right here watching you go on the rocket. There you go. You're definitely moving towards Andromeda. No, I'm not. I'm on the rocket. I'm not moving. Remember? If I look down at my feet and I see the origin, well, I'm not moving because the origin is right here. Therefore, I never displace myself. So what do I see? I see Earth going pew and Andromeda's going pew coming towards me. So how far did I travel? That is to say, what's the distance that I just traveled? 0. I didn't move. This is a totally, by the way, I'm not making this up. This is totally how it works. The distance that I moved in the rocket, no, I didn't move in the rocket. I sat down in the rocket, I sat there. I sat there, sat there, sat there, sat there, sat there. And then I got up and I walked out the door and I was at Andromeda. And how did I get here? I don't know. Andromeda was flying all the way over here. But I just stood, I stayed right where I was. You are completely within your bounds to say that. And therefore, to set this quantity equal to 0. That means I can figure out the time that elapsed on my watch on the rocket ship by subtracting the squares of those two things right there. So let's do that. Let's do that. Let's go with this, as it's going to see, you're going to go with 2.2 squared minus 2 squared. And then I'm just not going to write the times 10 to the 6th in here. But if you do that, then I'm going to go, all right, I'll just do this, and we'll go square that number, and we'll go minus 4. And I got 0.93. I have to then square root that thing. And I get 0.9, what do I get? 0.97, 0.94 or something like that. And then I have to square root this number. Oops, not S, T. So T rocket is then the square root of 0, that's a 9. Oops, I'm off the end of the board now. I need to watch what you're doing. Now delta T rocket, T rocket is now equal to 0.9 what did I say, 0.97? Say about 0.97. 0.97. But that's still times 10 to the 6 years. I'm off the end of the board. Sorry about that. Something like that. I think it was about 0.94, and then I have to square root that because I'm dealing with squared quantities here. And in order to find the rocket time, I just square root the whole shebang here, and I end up with 0.97 times 10 to the 6. So 970,000 years. It's somewhat unfortunate that I am long dead by the time I get there, and it is with great displeasure that the Andromedans open my rocket ship door with great anticipation to find my long dead bones sitting in the chair. So there you go. That's how you do a calculation involving the interval and different times. I want to go back in and fill in a little bit about what's going on with distances and times in special relativity. So, because so much of this is really wacky, since we have no conception of what things are like at these speeds, there are really no analogies that I can make. Oh, doing this is just like doing this other thing. This is kind of the beginning of the failure of those now. I've been able to do that most of the time throughout optics and thermodynamics, but now we're into this stuff and there is no comparable situation that I can refer to say, oh, when this happens, it's kind of like this thing over here. There just isn't, because we don't have any experience. There's nothing I can appeal to in your experience that would give you insight into how or why this is working. And so so we've left. That's it. Let's talk about time and space in special relativity. So I'm motivating, hopefully, that the coordinates of the points of me leaving Earth and me arriving at Andromeda are different. However, the linkage between them is the same space-time distance. Okay, so hopefully I'm motivating to you that these coordinates are different when you change frames, but when you do this strange procedure to them, it turns out that gives you the same number no matter what frame you're in. All right, so that's a really important thing. The interval is what's called invariant. It is like light speed. It's the same for all observers, okay? In special relativity, they all agree what the interval is. They disagree on what t and x are, but they agree that when you do this, you should get the same number as everybody else. Okay, so if I take a look at space and time in special relativity, I'm going to go back to a very simple way of keeping time. And it's so simple, in fact, that you'd say, well, anything I get, any conclusion I come to with this way of keeping time must be the same as more complicated ways of keeping time. So if I find something that's true here, it should be true for whatever other thing I'm going to measure with. All right. Let's imagine then that we have a train car. Okay, I'm going to draw a couple of versions of this train car. Let's suppose it's traveling left to right at some speed v. Okay, at some time later, it's here. Oh, that one's. Let's try this one. And at some time later, it's here. Let me just get rid of some of this so I can clean up and we can see what we're doing here. All right, hopefully, okay. Okay, hopefully the same train car and at 3 different snapshots of its journey left to right. The train car has a mirror right in the very center of it on the top of the ceiling right there. That is a mirror. And I'm going to install a very simple device on the bottom of the train car right below the mirror, and that is just a simple light bulb that can be pulsed on and off, and something that will detect the light as it bounces off the mirror and comes straight back down. I'm going to put here a kind of weird looking set of things, and one of them is an emitter and one is a detector, okay? So I'm going to say that the light comes out of here, hits the mirror, bounces down, and is detected by the detector. So this will be the bulb. I'll call this the bulb, and I'll call this the detector. Bulb and detector on one side or the other. And I'm going to draw that on each side of the train car here. The bulb is the top one, or the taller one, and then the detector is the smaller one. All right, if the train car has some height to it, which it does, the train car has some height h. If I am interested in the time it takes the light to be emitted, hit the mirror, and come back down and be detected, I should be able to say, well, that constitutes some amount of time. I'm going to call that 1 unit of time. And the light's going to, every time I go click, the light goes up, down, and I call that 1 unit of my time. And the time that it takes, of course, is really, really small in terms of seconds. But nonetheless, I'm going to call that my unit of time. Therefore, say the time, if I were to kind of just pulse this thing as best I could at a constant rate, or if I set up something that just pulsed the light, I had a little turntable with holes in it spaced equally or something like that, such that the light pulses up and down at constant intervals of time, then what I can do is say that the time between the light leaving the bulb and then being detected by the detector is going to be 2h divided by c. H up, h down, speed of light, right? I could say whatever units I want there. I'm going to say that's the interval of time between emission of the light from the bulb and detection of the light by the detector. All right. Okay, sound good? If I'm on the train car, it goes boom, boom, no problem. Now, I'm going to invoke the usual special relativistic idea. I want to know what it looks like from someone else's perspective. So I'm going to remain on the train, but I'm going to push you off the train. There, I just pushed you off the train. You're on the platform, and you're watching me go by in the train. What's the path that light takes now, according to you, on the platform? Okay. For me, in other words, it's straight up and then straight down because I'm just watching it go up and down. But what do you see as the train is going past? Well, I would say that it is somewhat like, let's see. Let me get something a little bit heavier here, like that. So imagine that you're looking at the pen here, and as I throw it and I catch it, it never leaves the plane of my hand, right? But watch it again. Well, I did that side because I went a little too fast. It still stayed above my hand the entire way because I didn't have to do anything to catch it. So the light does the exact same thing. It hits the mirror on the top. It goes like this. Let's do it this. It comes out of the bulb, hits the mirror like this, and then comes down and gets detected by the detector here, like so. Whoops, I kind of lost the end of it there. Oh, it suddenly became a very intense light beam. I would submit that this is the path that you see light taking. Because if I drew a whole bunch of other trains in between all of these right here, you would see that the light never leaves the plane of the emitter, the bulb detector mirror plane. It's always above it, right? It gets emitted, hits the mirror, and then goes straight back down and hits the detector. So that's the path I think that you would see. If the train travels, if the train travels a certain distance in this time, so here's the train distance, it's traveling at some speed v, and it takes some time to say get from here to here. Then delta t, right, as observed from the platform, this is going to be, say, d, should be 2d divided by c. Oh, I should probably note this as train. Where d is actually the hypotenuse of the triangle. This is not a space-time diagram. This is actually, we're looking at space. Therefore, d is equal to the square root of h squared plus v squared t squared. Right, so if the train is traveling some distance, this is a number which is greater than h. And therefore, this distance d is larger than h, which makes the time between emission and detection larger, as observed by the platform. So those of you who are on the platform watching, this is what you see. In other words, if you consider that the time between emission and detection is like a pulse of time, then you're saying that according to your perspective, my time is running slower, which means that the time between clicks gets longer, right? So instead of a second, I can hear the clock right there ticking. It goes tick, 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 tick. We all kind of have this approximate rhythm ingrained in us by now, right? About how much a second is, boom, boom, boom. Now what you're saying, my clock doesn't look like that to you. You're on the platform, you're seeing my clock going like this, boom, boom, boom. My clock is running slower, according to you on the platform. Not according to me. Looks just fine to me. I'm on the train. Looks slow to you. All right, so according to this, we get a common phrase, which is that moving clocks run slower. You'd say, that's not true. Clocks don't run anywhere. Quick, get after it. Wah, wah. In other words, time goes slower on a clock that is in motion with respect to you. And that's why when you look at the rocket time here, it makes sense from Earth's perspective that there's less time that passed on the rocket than what passed on Earth. Because according to Earth, that rocket goes, and that means the whole time I can look at the clock there and go, that clock's not running as fast as my clock is. It's not keeping the right time. It's keeping less time. But this could have been anything, right? I could have said it's your heartbeat, right? It's the time between the contractions of the ventricle things of your heart, the chambers in your heart going blah, blah, and blood pumping around. I could have said that. And this still would be true. So it's not an illusion. It actually is true that time is running slower for someone who's in motion with respect to you. That is to say, not only does it appear that their clock is slow, their time is actually slow. They are experiencing time at a different rate than you are. That's what this is telling us. And that is how time for moving clocks runs slower, which means that whenever you're in these situations here and there's the rocket going past, the rocket goes, the Earth observer goes, the rocket clock is slow, the rocket clock is slow. Yeah, and it's true. The rocket clock is slow. Therefore, I don't age as much if I'm in the rocket. I age slower than you do. Okay, which leads us to a fun situation here, which is known as the twin paradox. And this was the first, maybe not the first, one of the first rebuttals to special relativity that was put forth. And the rebuttal goes something like this. Imagine that you have two twins born on Earth, literally the exact same time, or at least close enough, near as you can make it, okay? We're not worried about things like pregnancy and birthing at this point. Just imagine they were born at the same time. Okay, fine. They are the exact same age. They grow up. They live here on Earth for 20 years. Okay, they are both 20 years old at the strike of the clock, at noon on a Tuesday, whatever. Okay, fine. So one of the twins now has become an astronaut, gets into the spaceship, blasts off, goes to a distant star, realizes that the inhabitants of the star are very hostile. They've been shooting at the rocket ship and they're trying to, okay. So turns the rocket ship around, heads straight back to Earth. Comes back to Earth. When the twin that was in the rocket gets back to Earth, what happens? Because, note, according to the Earth twin looked at the rocket twin's clock and said, your clock's running slow. So when you get back after traveling, the entire time your clock was running slow. You're going to come back having aged less than me. I'm going to be, 40 years old. You're going to be 30 years old. I'm just kind of making up numbers, but you get the idea. Strange. And they're still twins, but now they're 10 years different. Well, hang on a sec. The paradox rears its head here. From the rocket twin's perspective, rocket twin says, Well, I didn't go anywhere. Earth blasted off that way, turned around, and came back and hit me. And here I am back. So it was your clock who was running slow because you were in motion, and I looked at your clock, which was in motion with respect to me on the rocket, and I saw your clock running slower. So as it goes and then comes back, you were in motion with respect to me the whole time. Your clock is the slow one. Why have you aged 40 years and me 30 when your clock was slow? It's you who've aged 30 and me who've aged 40. You see the paradox? It's the disagreement of like, whose frame of reference are we to be believing here? How can the same analysis lead to two completely different results? There must be something wrong with special relativity. But it's okay. There isn't. It's a paradox. And the idea of a paradox is to present you with a seemingly intractable situation, but there is a twist. So I can try to outline the twist here for you as we just are finishing up. Yeah, should be finishing up here. So here we go. All right, this is Earth's frame. Here is the rocket's frame. Let's see, C would be there, so the rocket would be somewhat like, let's say here. Okay, there's the rocket frame. Reaches the distant star with hostile inhabitants here. Turns around, comes straight back, same speed. What did I do? 1, 2, 3, 4. 1, 2, 3, 4. Oops. All right, so it's going to be something like this. All right, comes back to Earth, something like that. I mean for those things to be approximate mirror images of each other. So the axis goes up like so. All right. This then, here, would be kind of like the T prime axis of the rocket, whereas then this here, I can't write it up here, but how about I write it over here? Parallel with that would be, for example, the T double prime axis, the inbound. Okay, that's the inbound side of the trip. That's the rocket trip then, according to, well, both Earth and the rocket, because the rocket sees Earth is going away and then approaching, which is exactly what Earth sees. Okay, now the problem comes in to the question of whose clock is the correct one. I'll show you this, and then I think we're going to have to stop and finish sorting this out next time. If I draw the x prime axes, I'm going to draw the x prime axis. The x prime axis goes here, about like there. Oops, that's not very dark. Hopefully you can kind of see that. I'll darken it in. It was about like there. Then, remember, every point along any line parallel with that occurs at the same time for someone on the rocket. Therefore, when the person arrives at the hostile star and they look back at Earth's clock, what do they see? They see, simultaneous with arrival at the planet or the star or whatever it is, they see Earth's clock as having, this time right here. That's the time on Earth according to the rocket when the rocket reaches the planet. Then on the inbounds journey, so wait, before I do the inbounds journey. So therefore you can see, I think you can see. So this is one of those times when geometry leads you wrong, because Euclidean, you'd look at it, you say, okay, well, wait. According to the Earth observer, the time on Earth was here when the twin hit the planet. But according to the twin that was traveling, Earth time was actually here. So that means the Earth clock is running slow according to the twin, right? Because the time is less. But according to Earth, what's funny to say here is that the time according to Earth here, which is a leg of a triangle, is less than the hypotenuse here. So this is not the longest leg of the triangle. It's kind of weird, but sorry about that. So the time experienced by the twin on the rocket ship between here and here in the blue line is less than the time between here and here on the black line. Therefore, the Earth twin says the rocket twin experienced less time. So the question is, and the same thing's going to happen on the inbound side. So the question is, how do we resolve this? It's a seemingly intractable situation, but never fear, we'll get to the bottom of it. But unfortunately, it's going to have to wait till next Tuesday because I'm not going to see you tomorrow. Good luck on the celebration. Make sure to show work. Make sure to give me reasoning. Don't just knock equations out and call that reasoning. I want to hear about your physics reasoning. That's the point of this class. As usual, I'm going to give you the honor system warning. You are on your honor system again. I assume you're all comfortable with this. No outside resources and no talking to other collaborations going on during the celebration. Okay. As usual, should I find otherwise, well, then I don't really want to talk about it because I know we won't deal with it. So take your time. Make sure to turn in something for every problem. Otherwise, I can't give you anything. All right. And keep calm and physics on. So good luck, and I will see you back here on Tuesday of next week for the hopefully thrilling conclusion of the paradox involving the two twins. All righty, folks. Enjoy your celebration. Enjoy your weekend. Talk to you then.
I had a question.